Before we get on with the lesson, let me go over the major theorems that we've done so far. So the orbit stabilizer theorem, if G is a finite group, the number of elements in the orbit of X is the same as the number of elements in G over the number of elements in the corresponding stabilizer. This is true for any element that you take from the set X. And then Burnside's lemma. For a finite group G acting on a finite set X with R number of orbits, we can define R to be the average of the number of fixed points of the elements of the group G, right? Which you can show by proving this given equality. And after that, we've done the fixed point congruence theorem. First, we defined a P group, that is a group G, where the number of elements in this group is some power of P for prime P, right? So this power is a non-negative power. So non-negative integer K. And we understand that when K is equal to 0, you have the trivial group. When K is non-zero, it's some non-trivial group. Then the fixed point congruence tells you if G is a finite P group acting on a finite set X, then we have the number of elements in this set X to be congruent to the number of fixed points modulo P. Okay. Okay, then we proved this corollary, which states that G is a finite P group acting on a finite set X, and in the proof we used the fixed point congruence. If the order of X is not divisible by P, then we must have at least one fixed point. On the other hand, if it is divisible by P, the number of fixed points must be a multiple of P, even 0. Right? Then last theorem that we went over, for a non-trivial P group G, the center ZG is non-trivial. We finished the proof of this also. So today I will state Cauchy's theorem. Excuse me. And we will move to conjugacy and class equation and the class equation. Cauchy's theorem. Now, we take G to be a finite group whose order is divisible by P. Then we say that G has an element of order P and also G has a subgroup of order P. I will disregard the proof of this one. You can try it on your own. For now, we will disregard it. Let G be a finite group let G be a finite group whose order is divisible by a prime P, then G has an element of order P and also has a subgroup of order P. Okay. and has a subgroup of order P. Right. Let's leave this for now and let me start with a very small topic, conjugacy and class equation. Conjugacy and class equation. Right. Now we already know the action of a group on itself by conjugation, right? So let's consider this action once again. Consider the action of a group G on itself by conjugation, which is denoted by, and the action is defined as G dot X equals Gx G inverse, right? We say that G acts on itself by conjugation, right? We say that G acts on itself by conjugation, and the orbit once again is defined to be, let me write, G is said to act on itself by conjugation. Now we define the orbit of X where X is any element in G. By definition of an orbit, this is G dot X for every G that you take from the group. Now observe that X is also an element in G because this action is on itself. And G dot X by definition is simply Gx G inverse, right? Now these orbits of elements of G are what we call conjugacy classes. We have actually gone over this as well. I will write it over here as well. The orbits, as a small recap even, the orbits of elements of G are called conjugacy classes, right? Now, let's consider an element A in G. And for this particular element, let's define its stabilizer, stab A. What sort of elements do we have? Every element G in G that fixes this particular A through the given action. In other words, where G dot A is equal to A. And we know that G dot A is defined by G A G inverse. Multiplying both sides by G, you get every G belongs in here such that GA is equal to AG. In other words, this is the set of all elements in G that commute with A. Here, we are taking all elements in G such that GA is equal to AG, where you can commute the two. In other words, you can write this as the set of all elements that commute with A. Now we say that step A is the centralizer of A, right? The stabilizer of an element A in G is usually known as the centralizer of, centralizer of A, the element A. Right. Now, we know by definition of orbits, orbits of a given set X, the orbits would partition the set. Now here we are considering a group which is acting on itself. So the set X in this case would simply be G. So we say that the conjugacy classes, which are essentially these orbits, right? They form or they partition G. Right? The same thing that we've learned so far with orbits, which are subsets of X, right? So I can write the conjugacy classes of a group G, partition the group G, right? Once again, for any group G, you can always find conjugacy classes. How do we do that? We simply define the action of this group G on itself by conjugation, right? That is taking G dot X equals Gx G inverse for every Gx that you take from G. Then for each element in G, you can find or define and find the respective orbits. These orbits for each element we call conjugacy classes, and we know by properties of orbits, orbits would always partition the given set. In this case, the set is the group itself. Therefore, we can say that the conjugacy classes of a given group G partition G. Right. Now we have a small theorem. Okay. Under the action of conjugation, we have for any element X that you take from the center of G, denoted by Z of G, right? You can always find it orbit, and this orbit would simply contain this one element X. Not only that, when you find the stabilizer of this element would simply be G. Right? Then the proof is very simple. Now observe that all these are if and only if statements. Right? So take an element X in Z of G, the center of G. If you take X from Z of G, by definition of Z of G, this is if and only if xg is equal to gx by definition of Z of G for all G in G, right? And what we do is we want to show that there is only one element X in the respective orbit. And the action in question over here is simply conjugation. So we have a group G acting on itself by conjugation. Under this, all these statements are true. This is if and only if simply taking G inverse on both sides. On the right, we have over here simply X equals G inverse, because G inverse is simply the identity. This is true for all G in G, right? By definition of the orbit contains, orbit of X contains all elements of the type G dot X. And when the action is conjugation, G dot X is simply Gx G inverse. Now what do we have? For every G, for this particular X, Gx G inverse is simply equal to X. In other words, G dot X is simply equal to X for any G that you take from the group. So what does it mean? By definition of the orbit of X simply contains this one element X, because no matter for which G you find G dot X, you would end up getting X, right? Now, on the other hand, if you try to find the stabilizer, right? The stabilizer gives you every G, we go back, right? Under conjugation, the stabilizer of X contains the set of all elements that commute with A. The set of all, the stabilizer gives you the set of all elements that commute with A. So for this particular X, we get the set of all elements G that commute with X. If you go back to this statement over here, it says if and only if X equals Gx G inverse. If you go to this very first one, for every G, Xg is equal to Gx. So every G, every element that you take from the group will commute with this particular X that you take from the center of G, right? So the stabilizer of X contains every element in G because every element commutes with this particular X. So we can simply write this is if and only if the stabilizer of X contains every element in G. So this must equal G because the stabilizer is always a subgroup of G. Okay. It's a very simple proof. Now the class equation. Okay. Let's take G to be a finite group. Then we know G is the disjoint union of a finite number of conjugacy classes. Once again, why do we have that? For any group G, we can always define an action by conjugation. So G would act on itself by conjugation. Under that action, we have orbits and we call those orbits conjugacy classes. If we go back just a few moments ago, I told the conjugacy classes of a group G partition G, right? So when G is finite, you have a finite number of orbits, right? So under this action conjugation, you have a finite number of conjugacy classes. And that finite number of conjugacy classes partition the given group. And we know from properties of uh, orbits, there are any two orbits that you take will always be either identical or disjoint. So we can easily see that G is the union of, G is the disjoint union of a finite number of conjugacy classes, right? So let me write down all that information. Let G be a finite group, right? Then G is the disjoint union of a finite number of conjugacy classes, right? Okay, now we know from the previous theorem, we know that when you take an element from the center of the given group G, this means that the orbit of this element is simply the singleton set X, right? Or the set containing only this one element X. This is from the previous theorem. I'll take this as 1, right? What does this mean? Every element, now observe, when X is taken from the center, it belongs, the orbit of that particular element is simply the singleton set. On the other hand, if the orbit of an element contains only that element, that means the element itself belongs in the center of G because it's an if and only if statement. So what does it tell you? Every element that you take from the center is in the conjugacy class containing just that element, right? That means every element uh, X that you take from the center is in the conjugacy class containing just that element, right? So if you look at the entire center of G, every distinct element makes up one conjugacy class. So we can see that the center of G is actually partitioned into the conjugacy classes of singletons, right? If you look at it, we can always write the center of G as the union of. If you take the union of these singleton sets where this X comes from Z of G, right? And we know that this singleton set is the orbit of itself, right? The singleton set is the orbit of X. So we see that you can write it as the union. Once again, remember, when X is taken from the center, the orbit of that particular element simply contains that element, and it goes the other way as well. Therefore, we can write Z of G is partitioned into the conjugacy classes of singletons. Singletons meaning these one element sets, right? Now, on the other hand, if you take an element that is outside of the center, right? From one, we understand the orbit must contain more than one element. If X is taken from the center, the orbit can only contain X, right? If the orbit, this is an if and only if statement once again. If the orbit contains that one element X, then it belongs in the center. So if you take an element outside of the center, if, let me put it this way, let X not be in Z of G, then by 1, right? This statement, we know that X, the orbit of X, or we can simply say the conjugacy class of X contains more than one element. Surely every orbit will contain that corresponding element. But in this case, because X is taken outside of the center, it must have another element which is distinct from X, at least one. So, right? So we simply say more than one element. Contains More than one element. Right. Now let's suppose now we are trying to build the class equation here, right? So we have elements that are coming from the center and elements that are outside of the center. If the element is inside the center, the conjugacy class contains just that element. If it is coming outside of the center, then the conjugacy class of that particular element or the orbit of that particular element must contain more than that element, more than one element, let's say. Okay. Now suppose suppose are conjugacy classes outside of the center. Outside of the center, right? Now remember, G is a finite group. So we can have finite number of such conjugacy classes. So let's take, now we have R number of conjugacy classes outside of the center. If you take all the elements that are in the center, we have all these singleton sets, which are conjugacy classes by themselves, right? So any element that you take outside of the center, let's suppose there are R number of conjugacy classes with respect to those. And let's take N1, N2 up to in R to be the number of elements in these conjugacy classes. Be the number of elements in these conjugacy classes, right? Then each ni over here must be greater than 1, right? Then ni must be greater than 1 for all I that is between 1 and r. Why is that? We are taking R conjugacy classes outside of the center. And we have argued so far, if this conjugacy class is coming outside of the center, coming from outside, it must have more than one element. And all these N1, N2 up to NR being the number of elements that are coming from, that are in these conjugacy classes outside of the center, they must be more than one, right? Now we know that G is a partition of conjugacy classes. So far in our discussion, we saw that, right? Then we can write the number of elements in G with respect to the number of elements in these conjugacy classes. Okay, let me put it this way. Right. Now, because G is a partition of conjugacy classes, we have the number of elements in G to be the number of elements in each distinct conjugacy class. And remember, some conjugacy classes are coming with respect to elements that are in the center, right? So we have where X is in the center of G. Oh, sorry. Let me put it this way. Let me put it this way. This is wrong. The number of elements in G. Now, like I told you, we have some conjugacy classes that are coming from elements that are inside Z of G, and each of those conjugacy classes have just that one element. So we have the order of G to equal the order of the center plus the number of elements in those other R conjugacy classes that are outside the center. So number of elements of those other conjugacy classes, we have taken them to be N1, N2, up to NR, right? So equivalent, the same statement we can write using the orbit stabilizer theorem. Orbit stabilizer theorem. The number of elements in G is equal to the number of elements in the center, where each element over here defines a unique distinct conjugacy class, plus using the orbit stabilizer theorem. For all G, we have the number of elements in G over the corresponding, the number of elements in the corresponding stabilizer. Where this G over here runs over each conjugacy class containing more than one element, right? Where G runs over each conjugacy class containing more than one element. Let me write it here. Where G runs over more than one element, right? And we only have to take one from each conjugacy class. So let me write taking one from each such conjugacy class. Okay, so once again, using the orbit stabilizer theorem, the order of G is equal, and we are applying it over here, right? Where N1 is greater than 1. In other words, it's an orbit containing more than one element, right? So what we do is we run over all elements in G which belongs to a conjugacy class containing more than one element. And from each such conjugacy class, we only have to take one representative. Because if you remember, two elements that are in the same, if two elements belong in the same orbit, their particular orbits are identical. They are corresponding, if you take the orbit with respect to those two elements, you get the same orbit, right? So we only need one representative from each conjugacy class. That's what I have written over here. Now, this is what we call the class equation, what you see over here. Class equation is given by order of G, where it's finite, is equal to the order of the center plus this summation order of G over the corresponding, the order of the corresponding stabilizer, where G runs over conjugacy classes containing more than one element, taking one from each such conjugacy class. Right. Okay, do you have any questions so far?
No, ma'am.
Okay. Now we have a small theorem. If G is a finite P group of order Pn, let me write it. If of order Pn, where n is greater than or equal to 1, right? Now it's a P group uh, of order Pn where n is greater than or equal to 1. This means that G is a non-trivial P group, right? Because n is the least, at least 1. Then we have the center of G center of G to be non-trivial. The center of G to be non-trivial. It has to be, so in other words, what does it mean? It means it contains more than one element, right? That is exactly what we have to show in this case. Okay. Right. Now, G is finite, and from the statement itself, because n is at least 1, we know that G is non-trivial. Therefore, the order of G is greater than 1. It has to have an element other than the identity, at least 1, right? So let me write it all out. G is finite and order of G is this, where n is greater than or equal to 1. Therefore, the order of G is greater than greater than 1. It has to have more than one element, right? Hmm. Okay. Now, uh, we can consider two cases. One is when the center of the group is simply equal to itself, and the other case when it's not equal to the group itself. If the center of G is equal to G itself, then obviously the number of elements in the center is more than one, because the order of G is more than one. Therefore, we conclude this is also non-trivial, right? So if the center of G, which is a subgroup of G, is equal to G itself, there's nothing to really prove, then order of Z of G is simply the order of G, which is greater than 1, right? And therefore, Z of G is the non-trivial subgroup of G. It's simply G, it's non-trivial, the result is true. So let's assume now that Z of G is not equal to G. It's a proper subgroup, right? Therefore, let's assume the center of G is not equal to G. So it's a proper subgroup of G, right? We know from a previous theorem, if you take an element from the center, then the orbit of that corresponding to that particular element contains just the element itself. Not only that, the stabilizer of the corresponding element must equal the entire group G, right? What I'm referring to is this theorem, right? If you take one element from the center, then the stabilizer is equal to okay. So we know when x is in the center, when x is taken from the center, this is if and only if the stabilizer of x, the corresponding element, is equal to G, right? If x is taken from the center, the stabilizer is equal, the corresponding stabilizer is the group itself. On the other hand, if the stabilizer of the corresponding element is equal to the group, then that element, corresponding element, is taken from the center, because this is an if and only statement. What does it tell you? It tells you any element that you take outside of the center, corresponding to that, we can find the stabilizer, and the stabilizer cannot be G, right? Then for any element G that you take from the center, we must have, any element G that you take outside of the center of G, outside of the center of G, we have the corresponding stabilizer of G to not equal G. This is because what you have above is an if and only statement. Right? Stabilizer of G is not equal to G. So we must have the number of elements in G over the number of elements in the corresponding stabilizer to equal P to some power of K, once again for K greater than or equal to 1. Why do we have this? Remember, the stabilizer of any element is a subgroup of G. G is a finite group now. By Lagrange's theorem, the subgroup must divide the order of G, right? The subgroup, the order of the subgroup must divide the order of the group G. And the group G is a P group, so its order is some power of P, which is a prime number. Therefore, the order of G divided by the order of its subgroup must equal some other power of P. Okay? Right. So if you go back to the class equation above, right? If you go back to the class equation, if you look at the class equation over here, we see that this G is taken outside of the center, right? So for each G that you take from outside the center, the term that you see over here, order of G divided by the order of the corresponding stabilizer, must be divisible by P. So in the class T equation, in this summation, each term is divisible by P, right? So let me write it down. Then we understand that P divides each term in the summation of the class equation. Right? And not only that, if you go here, right? So once again, back at the class equation, every term in this summation is divisible by P. G is a P group, its order is P to the power of N. And because N is at least 1, the order of G is at least P or some other positive power, right? Therefore, the order of G is also divisible by P. So all in all, we see that this side is divisible by P, this summation is divisible by P. So take it to the other side, the difference is divisible by P. What does it say? It says that the order of the center must be divisible by P, right? So we write oh, sorry. I can write also P divides the order of G, which is equal to Pn, and hence from the class equation, P divides the order of the center. P divides the order of the center, and we know that Z of G is a subgroup of G, not just any subgroup, it's a normal subgroup of G, which we have seen and proved. This implies that the order of, because it's a subgroup, and P divides this order, the order of Z of G must be some power of P, right? For R between 1 and N, right? In other words, Z of G has at least, Z of G has more than one element because its order is divisible by P. Therefore, it has more than one element. So we conclude it cannot be the trivial subgroup of G which contains just one element. Okay.
Yes, ma'am.
Right. Right. With this, we move on to another proposition. Um, okay. Let G be a group then we say that G is abelian if and only if G over Z of G. So we are talking about the quotient group when you take the quotient with respect to the center. Remember, center of G is a normal subgroup of G's. This quotient is well defined. The quotient group is cyclic. Right? So G is if G is abelian, this quotient group is cyclic. On the other hand, if the quotient group is cyclic, G must be abelian. Right? First, let's suppose that G is abelian. First, suppose that G is abelian. Then we have the center of G, right? Which contains elements in the group such that Gx equals Xg for all X in G. So we take elements from G that commute with every other element in G. And we know that Z of G is a normal subgroup in G. Therefore, like I told you earlier, G over ZG, this quotient group, is a well-defined quotient group. Is a well-defined quotient group, right? If G is abelian, right? What can you say about Z of G? if G is abelian. That means any pair of elements that you take from G would commute. If G is abelian, you take for any G, for any X that you take from the group G, Gx would equal Xg because G is abelian. So what does it say? We must have the group G to equal its center. In that case, this quotient G over Zg, because Z of G is now equal to G, the quotient itself would give you the trivial group containing only the identity, and in the quotient, the identity would simply be Z of G, right? And because it's containing that identity element, but it's simply a cyclic group, right? So we are done in that case. Let me write. If G is abelian, then uh, the center of G is equal to G itself. If you look at the definition, we take every G in G such that Gx equals Xg for all X in G. G abelian means any pair of elements would commute under the binary operation, given binary operation, right? So in that case, the center of G is equal to G, in which case the quotient G over Z of G containing all left cosets of, for your reference, I'll just put it over here, right? Uh, is simply the trivial group. So in this case, you're taking the quotient of G by itself, okay? The trivial group containing only the identity element Z of G. In the quotient group, this is the identity element, right? And we take every other non-trivial left coset of that. Now, but in over here, because Z of G is equal to G, when you take the quotient of G by itself, we end up getting the trivial group. Then we see that G over Z of G is simply containing this identity element Z of G. This is generated by the identity element, right? A cyclic group. So when G is abelian, we see that the quotient is a cyclic group. Now, on the other hand, let's suppose the quotient is cyclic. Now, suppose that the quotient G over Zg is cyclic, right? Let's take two elements, X and Y from G. Since this quotient is cyclic, now we want to show that G is abelian. So we want to show at the end that xy is equal to yx. That is what we are aiming for. X and y are chosen arbitrarily from G. Given that this quotient is cyclic, we want to show that G is abelian. In other words, xy is equal to yx. Now, this is cyclic. Therefore, every element in here will be generated by a single element. Is generated by a single element in the sense will be a power of that element. Any element that you take from the quotient is cyclic. Since this quotient is cyclic, there exists an element G in G such that the quotient is generated by G times ZG. Now remember once again, what sort of elements do we have in the quotient? The set of left cosets. Sorry, the set of left cosets of this center. So every element is of this type. So, and because it's given to be cyclic, for some particular G that you take from the group G, the entire quotient is generated by G times Z of G. The left coset of Z by this element G. Okay. Now, X and Y are taken from G. So for X in G, we know that X times Z of G is an element in this quotient, right? Is an element in this quotient. So it has this particular element, which is the left coset of Z of G by X, is an element in the quotient. It has to be some power of this generator. So I'll write it as G to the power of K1 of ZG, right? And similarly, if I take this to be 1, we'll write, then we have by 1, X of Z, X times Z of G to be this, and Y times Z of G to be G, the some power of this generator. When you say some power of this generator, we have seen in our previous classes, you take the power of G times Z of G to K1. That simply means G to the power of K1 times Z of G. Okay. So this will take to be the power K2. This implies this implies X is equal to GK1 and some Z1 that comes from this center, and Y is equal to G to the power of K2 times some Z2, which also comes from the center. For some Z1, Z2, that is in the center. Now let's compute xy. Now let's find xy. Now xy is equal to, x is given by g k1 z1 by g k2 z2. Okay, now this is equal to GK1. We simply commute these two elements. I'll tell you why. We can commute Z1 and GK2. We have GK2, Z1, Z2. Why do we have this? Observe, we are taking Z1 from the center. What sort of elements do we have in the center? Elements that commute with every other element in G. Elements that commute with every other element in G. So I can write because Z1 is in the center, meaning, and this implies that Z1 GK2, GK2 is equal to G to the power of K2 Z1, right? By definition of the center. Now this is equal to, we simply add these two powers, K1, K2, Z1 times Z2, right? This is equal to K1, K2 are integer powers. And we know integers under addition, it's an abelian group, so we can commute those two. Instead of writing K1 plus K2, I can simply write K2 plus K1. And take, I'll just put K2 plus K2 plus K1, Z1, Z2. This I can write as GK2, G to the power of K1, Z1, Z2. Once again, okay. Now what we are going to do is, G is a group. So using the associativity and the fact that Z2 is in the center, right? I will simply group these two so that you can easily see this. I will commute these two. Why is that? Let me first write it and write the reason after that. G, K1, Z1. This is because we have Z2 in the center. That means this element would commute with any other element in the group. And so we have GK1 times Z1. G to the power of K1, Z1, they are both, Z1 is taken from the center of group. In other words, it's a group element. These two are group elements, so their product under that, whatever the binary operation, is also an element in the group. This is an element in the group. You're taking this, we apply the binary operation between this element and Z2. Z2 is taken from the center, so it commutes with any other element in the group. So these two would commute. You have Z2, Z1. Right? This is the reason. And this is equal to, I will write over here, GK2Z2 is Y, GK1Z1 is X. Right? So we have XY to equal YX. By definition, G is abelian. X and Y are chosen arbitrarily. Therefore, G is abelian. And the result follows. Okay, one more theorem before we actually get to rings and fields. Okay, any group of order p squared, where p is a prime number, must be abelian. Right? Let me state it. Any group of the p squared is abelian. Where p is a prime. Where p is a prime. Okay. Right. So we have a group G of order p squared. In other words, it's a p group by definition, right? So let me take, let G be a finite. It's finite. P squared is a finite number. Finite p group where its order is simply equal to P squared, right? So P is a prime, order of G is P squared. It's a finite group. It's a non-trivial finite P group. We have to show that G is abelian, right? Let me write. P is prime. We have to show that G is abelian. We know that the center of G, which contains every element in G that commutes with every other element that you take from the group, is a normal subgroup of G. And by Lagrange's theorem, the order of the center must divide the order of the group G, right? We know that the center of the group G is a normal subgroup of G. Then by Lagrange's theorem, order of the center must divide the order of the group G. Now observe, since the order of the group is P square for prime P, right? Then since the order of G is P square, the order of Z of G can only be a certain, we can take only certain values. It could either be 1. Now remember, the order of Z of G, order of the center must divide P square. P is a prime number. So the order of the center could either be 1, P or P squared. Those are the only possibilities. The values of this order of the center should take is either 1 P or P squared. It's either 1 P or P squared, right? Now, obviously, we can't have the order of Z of G to be 1. Why is that? If you look at the theorem, this previous theorem, if G is a finite P group of order Pn where n is greater than or equal to 1, right now we have a P group of order P squared. N in this case is equal to 2. Then what do we have? The center of G to be non-trivial. It must have, if it is non-trivial, it has more than one element. It has more than one element, right? So from that previous theorem, because G's order is P squared, the center of G is non-trivial. So its order must be greater than 1. So it cannot equal 1. So we can disregard the first one, but we have to write it. So let me write order of Z of G is not equal to 1 as the order of G is equal to P squared, right? This is because if G is a finite P group, of order Pn for n greater than or equal to 1, then the center is non-trivial, right? The center is non-trivial. Okay. Now if we take the order of the center to be P, right? Let's take the order of center to be P. Let the order of the center be P. Then what do we have? Then we have order of G over Z of G to equal which is simply p squared over p. This is because G is finite. And this the value of this is simply equal to p. Then what do we have as this is the order of the quotient. The order of the quotient, because G is finite, we can write it as the order of G over the order of its normal subgroup. In this case, we are simply talking about the center. This is equal to the order of G, which is p squared over p. You divide, you get p. In other words, the order of the center, the order of this quotient group is a prime, right? The order of is a prime p. Then we must have, because its order is a prime, we must have this group to be cyclic. Therefore, from this, because its order is prime, this is a cyclic group. And we go to the proposition that we just finished, which tells you if G over ZG is, if the quotient is cyclic, G must be abelian, right? So we simply conclude that. Then the quotient G over Z of G is cyclic. Therefore, G is abelian. Let me write above proposition. Okay, this is when the order of the center is equal to P. We end up getting G to be abelian, exactly what we wanted to prove. Now, the last case we have to consider when the center, the order of the center is simply equal to P squared. Then there's actually nothing to really show. It's very easy to see. Let the order of the center equal p squared. Then what does it mean? The center is equal to the group G. We must have G to be abelian, but we can see this easily. Then we can justify this. Then Z of G is equal to G, as the center itself is a subgroup, just a normal subgroup of G. Therefore, G is abelian. Why is that? Once again, if you consider the quotient, G over Z of G, as we have seen before in our proof, this simply gives you the trivial group which contains the identity of the quotient, which is Z of G. We can write it as a cyclic group. Referring to the previous, we can write it as the cyclic group generated by its corresponding identity. Referring to the previous proposition, we conclude G is abelian. Do you have any questions?
No, ma'am.
Right. That's the end of all the topics that we are supposed to do with respect to group theory. With this, we can actually start rings and fields. Okay. Now, so far in group theory, in groups, in a group, we only have to study one binary operation, right? But when it comes to rings, we can actually think of it as this, it's sort of like a study on sets where two binary operations are involved, two binary operations are defined on the same set, right? For example, the integers. Addition is there, multiplication is there. Likewise. So let me formally define a ring. Mm. Definition, a ring usually denoted by R referring to the set, addition and multiplication, the two binary operations, right, is a set R together with two binary operations addition and multiplication, right? We simply call them two binary operations denoted by plus and this dot. We usually call them addition and multiplication, right? Uh, Let me write it, which we call addition and multiplication. Defined on R such that the following axioms are satisfied. Such that the following axioms are satisfied. First of all, R together with addition must be an abelian group. First axiom is we must have, let me write it, put one and write, R together with addition is an abelian group. Second one is multiplication, which is defined on R now, denoted by this dot, must be associative, is associative. Third option is the distributive laws corresponding to addition and multiplication must hold. If I write them out, for all A, B, C that you take from this set R, we must have A dot or A times B plus C to equal A times B plus A times C, right? Now remember the order in which we write these elements, we don't change because multiplication itself doesn't have to be commutative, even though addition is, because R together with addition is an abelian group. And the second one is A plus B times C must equal A times C plus B times C. The left distributive law and the right distributive law. We already are familiar with several rings, right? If all these axioms are satisfied, this system we call a ring. And when you understand addition, multiplication with respect to a particular set, we don't have to write the ring in this format. We can simply disregard writing it, abuse notation to some level and say R is a ring. When you say R is a ring, that means you understand what addition means, multiplication means for this particular set R. So these are some examples that we are somewhat familiar with. Z together with usual addition and multiplication is a ring. We know Z together with addition is an abelian group. We have seen this. Multiplication we know is associative, and these distributive laws hold. Not only that, the multiplication is a binary operation defined on Z because it's closed under multiplication. Take any two integers, you multiply, you get another integer, right? So Z and set of complex numbers, once again, usual addition, multiplication defines a ring. These are some of the rings. Now the other notation wise, uh, we will simply use AB instead of A dot B when denoting multiplication. Instead of A dot B. Right. Now let's take a look at another example. Let's take R to be any ring, right? So addition is defined over there. Multiplication is also defined for elements in R. Let's take this to be any ring, right? Let's take this to be any ring. And let's denote by Mn of R, right? N by N matrices or matrices of order N having elements of R as entries, having elements of R as entries. Then we can see that Mn of R under addition is an abelian group Why is that? You take any two matrices of the same order n, all those entries are coming from R. Over here, addition refers to the usual matrix addition. You take the two matrices, you add the two matrices. Because they are of the same order, addition is defined. So this is usual matrix addition. When you add corresponding elements. So the element at the first row, first column will be added to the element at the first row, first column in the other matrix. When you add those two elements, in that case, addition over those two elements would be the addition that is defined over this R, because all these elements come from this particular R, right? For example, is an abelian group. I'll leave out all the details to you, but I'll explain using just a small example. If we take M2 of R, right, this contains elements of this is an example now. Elements of the form A, B, C, D. It's an order two, it contains all order two matrices where A, B, C, D come from R. R is any ring, right? Now you add the two matrices containing elements A1, B1, C1, D1, A2, B2, C2, D2. Once again, A1, B1, all these entries come from R, which is some ring, right? When you add these elements, the usual matrix addition, you add corresponding elements, right? You add corresponding elements. So we have as the first entry A1 plus A2 right? What does this plus refer to? This plus would refer to the addition defined over R, right? A1, this plus would be the addition that is defined on R. Would not be the same addition that we are used to over integers, over reals, likewise. Could be maybe addition in Zn, where we consider the addition to be addition modulo n, right? So you have to be careful. This addition over here between these two elements would refer to the addition that's defined on R. We have B1 plus B2, C1 plus C2, D1 plus D2, right? Once again, you get a matrix of order 2 entries from R. This addition defined on R, on the ring R, okay? You can work it out and see that this is indeed an abelian. It is indeed a group, first of all, closed under addition. All these entries once again belong in R because R is an abelian group under the addition that's defined on it. Associativity laws hold. It's an inherent property. We know that matrix addition is associative. And the additive inverse is there. For A1, the additive inverse is negative A1. It exists in R as well because R is a ring. Likewise, you can see all conditions are satisfied, and you can clearly see that this is abelian if you take these two, A1 plus A2. You can commute these two. You can commute each of those entries with the corresponding elements that are taken from R. For example, A1 plus A2, you can write as A2 plus A1 because R is an abelian group under addition. Okay, so once you commute these two elements and you separate it into two matrices, you will see that you have commuted these two. So work it out on your own. We see that this is an abelian group, right? And it's the matrix multiplication, that we consider the usual matrix multiplication, but once again, when you come into these entries, multiplication between two entries would be the multiplication that's defined on R. So it's easy for us to see, not really easy, you have to work it out, but we can see that Mn of R is a ring under the usual matrix multiplication and addition. Under the usual matrix multiplication and addition. Okay. Okay, let's take a look at some other example, some other set. Let's consider a set that you're familiar with. Let's take n to be any integer, and we have seen that n times z is the cyclic subgroup of z, and we know that all subgroups of z takes this form, n times z. Cyclic subgroup of z under addition, right? Under addition. So we know that nz is a group on its own under addition, not just any group, it's an abelian group, right? We know that nz together with addition is an abelian group. It's an abelian group. Now, to see that this nz is closed under the usual multiplication, right? Let's take any two elements from nz. Let's take them to be nr and nq from nz. This implies that nr times nq, the usual multiplication, we can simply write as n times nrs. Now nrs, because n, r and s, they are all taken from z. Z is closed under multiplication. This product is an element in z. So n times an element in z is an element in nz. So it's easy for us to see that this product is an element in Z. So that is closed under multiplication. Right? It's
Madam,
closed.
that NRQ, like that.
I'm sorry.
That NRQ indicate like you have written in RS.
Yes, I'm very sorry. It has to be NRQ. NR times NQ, N times RQ. Sorry about it. NR and NQ. Yes, thank you. So NZ is closed under multiplication, right? And multiplication, because the set of integers together with the usual addition and multiplication is a ring, the multiplication that's defined on Z is associative and the distributive laws hold. And observe that n times z is a subset of this set of integers. Therefore, the associativity of multiplication and the distributive laws also hold in nz as well, right? They are sort of like inherent properties from the set of integers. So I will simply write the associativity of multiplication and distributive laws hold. Therefore, I will simply write nz is a ring instead of writing it as sort of like a system. Nz plus multiplication is a ring. I will simply write nz is a ring because we understand addition is the usual addition of integers. Multiplication is also the usual multiplication of integers. Okay. Now let's take a look at another example. Consider the cyclic group Zn together with the binary operation addition modulo n. If you remember, this we call addition modulo n. What sort of elements do we have in Zn? All elements from 0, 1 up to sorry, n minus 1. So in Z5, we will have 0, 1, 2, 3, 4. Likewise, right? And the binary operation is addition modulo n. We know that this is a cyclic group. It's a binary group under addition modulo n. Now, in order to see that this is a ring, we need to understand how multiplication looks like. What we are going to do is we will define multiplication on this set so that when you take two elements from the group, you take the product, you should get an element inside the group. What sort of elements do we have? Elements from 0, 1 up to n minus 1. But this is how we are going to define. Now, let's define for A, B in this group Zn, the product AB as the remainder of the usual multiplication product of the integers A, B, where the product AB as the remainder of the usual product of the integers AB when divided by n. When divided by n, right? And we can see that Zn is closed under multiplication. What does this all mean? Let's take a look at one example and let's see why we can do this for the general case as well. If I take Z5, this contains elements 0, 1, 2, 3, 4, right? So let's take 2 and 4 elements from this. How do we define the product 2 times 4? I will write it as 2 times, and under this cross I will simply put 5, right? This is to show that this is only to define or note down the definition that is given over here for multiplication. We are going to take these two integers, multiply these two. So 2 times 4 is 8. Now divide it by the corresponding n. Divide by 5, take the remainder. You have 2 times 4, 8. 8 you divide by 5, take the remainder. The remainder is 3. So 2 times 4 under this multiplication gives you 3. This we call multiplication modulo 5. In this case, multiplication modulo 5. Take the two integers, multiply, divide by 5. Why do we divide by 5? Because we are considering Zn. If it was Z8, we divide by 8. If it was Z10, we divide by 10 and take the remainder. So multiplication modulo 5, you have 3. 3 is an element in here. Right. So we understand how it is done. Right. Let's do one more example. If we take 4 times 4, right? 4 times 4, 4 multiplication modulo 5 with 4. 4 times 4 is 16. Divide by 5, take the remainder. You have 1, right? Why can we write this? Right. Obviously, we understand how it's done, but we simply use the division algorithm, right? You don't need to write it down. This is for all to see why this would work out for the general case. This is not really needed. This is as some extra for you all to understand this more. 2 times 4 is 8, right? So we can write 8 as 1 times 5 plus 3. What does this tell you? When you divide 8 by 5, you have one of those 5 inside, 3 in the remainder, right? Same over here. 4 times 4 is 16. Divide 16 by 5, you have 3 of 5s in there. 1 as the remainder. Now observe, in each case by division algorithm, the remainder will always lie between 0 and it will either be 0 or any of the integers between 0 and the divisor. In this case, this remainder must be between 0 and we divide by 5. So 5. Over here also like this, 0 less than 5, right? Using division algorithm, it's easy for us to see Zn is closed under multiplication modulo n, right? Let me write it out. This is not x, this is multiplication. It just got a little bigger. It's multiplication. Multiplication modulo n, right? So from division algorithm, we see that if you take AB from Zn, right? By division algorithm, consider the product AB. When you divide this by n, you can find the quotient Q times n plus the remainder R, where R lies between this range. R is in this range and less than n. What sort of elements do we have in Zn? All integers from 0 to n minus 1. Over here, this remainder, whatever the remainder that you get, will always be an integer from 0 to n minus 1, including 0, excluding n. So in this range, it could either be 0, 1, 2. You have the option of getting until n minus 1. Right? Therefore, we see that R is in Zn. So it's easy to see that Zn is closed under this corresponding multiplication. Zn, sorry, this is closed under this multiplication modulo n. This group is an abelian group. We have already seen this. And the distributive laws also hold. It's up to you to check it. I will simply write that this is a ring. Together with addition modulo n, multiplication modulo n is a ring. You can simply disregard writing plus sub n multiply sub n. We can simply write it as Zn plus multiplication, disregarding writing n, because now we understand in this group, addition simply means addition modulo n, multiplication simply means multiplication modulo n. So you don't have to worry about the subscript anymore. Okay. So sum notation. Okay. By 0, we will always note the additive identity of the ring R. We'll always denote the additive identity of R, right? And for any element A in R, the additive inverse, because R under addition is an abelian group, the additive inverse exists for every element, right? So the additive inverse will be denoted by negative A. This will denote the additive inverse, right? Okay. And then say we add A, n times A plus A plus A. Suppose we have n of A terms in here. In other words, n summands. We can write this as n times A. Now observe, this should not be taken as multiplication of n and A, right? We might have n, we might not even have n to be an element in the given ring R. Therefore, this n times A does not necessarily mean multiplication between these two numbers. So you have to be very careful with that. For example, I'll just write it not to be taken as multiplication of n and A, as n might not even be in R. For example, if you take 2 from Z3, right? 2 plus 2 plus 2, let me say plus 2, you can write as 4 times 2 because you have 4 of these. But does it mean you're taking the multiplication of 4 and 2? No, because 4 is not an element in Z3. This simply means you are adding 2 4 times. This 4 simply belongs to the set of integers, right? You are simply adding 2 4 times. This does not mean you are multiplying these two elements that are coming from here. It's not always true. Okay, now the other one is for uh, n less than 0, for negative n times A would simply be negative A added to itself n times, right? So you have n modulus sums, right? On the other hand, and this is when n is greater than 0. This is when n is less than 0. For n equals 0, we have 0 times A, right? Or we add A 0 times. That's the idea. Is equal to 0, right? So 0 over here refers to an element in the set of integers. This 0 is simply the the additive identity of R. It's the additive identity of R. Okay, keeping all these in mind, let's move on to the first theorem. If R is a ring with additive identity 0, then for any AB in R, we have 1, 0 times A is equal to A times 0 equals 0. 2, we have A times negative B is equal to, here negative B refers to the additive inverse of B, okay? Negative A times B equals negative AB. Negative A times negative B is equal to AB. Now, for familiar rings, for example, Z, R, we know, we understand multiplication, addition over those rings perfectly because we've been working on them for a long time. So with respect to those strings, it's easy for us to understand it. And not only that, these might seem a little bit trivial even, right? But not so for every ring. That's why we are writing it as a theorem and going to prove it. So the first one, okay, we had to show that 0 times A is equal to A times 0, which is equal to 0. First, what I'm going to do is add A times 0 to itself, right? A times 0 plus A times 0. Using distributive laws for a ring, what I'm going to do is factor out A. So we have A times 0 plus 0. This means A times 0 plus 0. 0 is the additive identity. When you add the identity to itself, you get the element. So you have 0. A times 0. Now what I'm going to do, this I can write as A times 0, which is an element in R. To this, I will add the additive identity, right? By definition of the additive identity, the addition of these two simply gives you A times 0. Now, we know that R is an additive group, right? So, using the cancellation law, in other words, taking the inverse of, additive inverse of A0 from both sides, we see that A0 becomes 0. Yes, we are simply applying the additive inverse of A0, that is negative A0 on both sides by cancellation law for the additive group. Here we use the cancellation law for this additive group. We cancel out A0 from the right on both sides. Additive group R plus, we have A0 to equal 0. A times 0. Similarly, we can show that 0 times A also ends up being 0, right? So I'll write likewise 0 times A is also equal to 0. You do the same thing. Instead of writing A0, we write 0 times A. That's it. Now to prove the second one, A times negative B is equal to negative A times B equals negative AB. First, we must understand the additive inverse of AB is simply given by negative A times B, negative AB. Okay. So first observe that AB plus negative AB is equal to 0. In other words, this is the additive inverse of AB. This is the additive inverse of AB. Now, we have AB. So, and remember, this is the additive inverse of AB. The inverse of AB is unique for that element. So, if you get another element, AB plus whatever element equals 0, the additive identity, that element must also be the same additive inverse. So, that is what we are aiming for. So, now, we have AB plus A times negative B. If we show that this entire addition is equal to 0, because the additive inverse of AB is unique, we must have this to equal A times negative B, right? So now this is equal to factoring out A using those distributive laws. We have B plus negative B. And we know that negative B is the additive inverse of B. So by definition, this is simply 0. A0 is simply equal to 0 from 1 above, right? From 1 above. Therefore, this means A times negative B is the additive inverse of AB. In other words, this must equal negative AB because the inverse is unique to the element. Therefore, negative AB must equal A times negative B. Similarly, we can show that negative A times B. To this, we add AB. Factor out B. We have negative A plus A. Factoring out B. Negative A plus A, because negative A is the additive inverse of A. This gives you a 0. 0 times B is 0. Once again, by 1 above, we just, the first one we proved. The same reason. The inverse of an element is unique to that element. Therefore, we must have negative AB, which is the additive inverse of AB, to equal this, negative AB. So we have negative A times B to equal A times negative B to equal negative AB. Simply put parentheses, okay. Now to prove 3, which is this, negative A times negative B is simply AB. Let's start off with negative A, negative B. From A above, I'm going to factor this negative out. So we have negative A times the second element, negative B. This is by 2 above. Now what do we do? Over here, I will factor out the negative. So I have negative AB. This is also factoring out in the sense simply using the one that we just finished proving, 2. Okay. Now observe that the additive inverse of negative AB is simply the negative of that element, negative of negative AB, right? If you go up over here, the the additive inverse of AB is negative AB. On the other hand, the additive inverse of negative AB must be AB. Therefore, what do we have? We have AB to equal negative of negative AB. Since AB is the additive inverse of negative AB. This is because AB plus negative AB is equal to 0, right? So AB is equal to negative of negative AB. Therefore, we have negative A times negative B, which is equal to negative times negative AB to equal AB. Right. Do you have any questions?
No, ma'am.